Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on concepts related to stress. And in the last class, we said that we want to find out what happens in an arbitrary plane. So, we took out a tetrahedron from the three-dimensional model. In the limit, the tetrahedron was shrunk to 0. You already know how to write the forces acting on the sides of the tetrahedron. You know the stress component. And you can find out what is the force in the x direction by simply multiplying by the area. And when we come to the negative x plane, you have the stress as sigma xx and the area is written as ANX. We did this and got the final expression in one fashion. But in the last class, I also wrote the final expression in a different manner. Not all of you have noticed it. Now, let us read this expression. We got this as Tnx equal to sigma xx nx plus tau yx ny plus tau zx nz. Like this, we determined it for all the three directions. But when I summarized it, I wrote it in a different fashion. I am happy that at least one student noticed it. What I had written is Tnx equal to sigma xx nx plus tau xy ny instead of tau yx. Similarly, I have put this as tau xz nz instead of tau zx. Writing it in this manner helps me to write it as a matrix notation. I do it on the strength that tau xy equal to tau yx, which we will prove. You have to wait for a class. That principle is known as equality of cross shears. Fine. Because the concepts related to stress or you have to go back and forth to understand it fully. So, using the equality of cross shears, the equations are rewritten in this fashion, which is convenient for me to write it in a matrix notation. And what we said was, even though my interest is to find out stress factor on any arbitrary plane, what is fundamental at the point of interest is a matrix of 3 by 3, which I also said it is representing stress tensor and the rank of this tensor is 2. Here again, to emphasize that I am able to write this using the principle equality of cross shears, which we will prove in the next class. And what is important is, when I have this, we are always interested in looking at the stress factor as a composition of a normal stress and a shear stress. Because later on, when you go and look at theories of failure, some theories use the normal stress as a criteria to judge. Theories related to ductile materials wants to find out what is a shear stress. So, we need to know how to find out these quantities. I can find out the normal stress as simply a dot product of Tn dot n, and when I do this, I get this as nx Tnx plus ny Tny and nz Tnz, which you can also write it down in longhand. I will also show it because you know what is Tnx, Tny and Tnz. So, when I multiply by this, I get a very nice expression. The normal stress is related to sigma xs nx squared plus sigma yy ny squared plus sigma zz nz squared plus 2 tau xy nx ny plus 2 tau yz ny nz plus 2 tau zx nz nx. Now if I want to find out the shear stress, it's easy for you to write the shear stress on the plane n is nothing but square root of T squared n minus sigma squared n. And this is a basic expression, and you can coin a variety of problems. At a point of interest, you will know what is the stress tensor, and for any given arbitrary plane, you would be in a position to find out the stress vector. Once you find out the stress vector, on that plane, you can find out the normal stress or the shear stress. You can also have class of problems wherein I want to find out the orientation of the plane. That means I want to find out what is the direction cosines nx, ny and z in a manner that on a plane you have only normal stress. So you can have two category of problems. For a plane, find out the stress vector using the stress tensor, or by dictating what should be the stress vector on the plane, determine the plane. You have both these class of problems, and you should be quite comfortable when handling these equations. You can have equally inclined to plane. That's very important from further studies. That is also part of your tutorial problem. Fine. And now we will restrict ourselves to 2 dimensions. And the moment I go to 2 dimension, I have a pictorial representation. I want to show what is the x plane. I want to show what is the y plane. I want to write what are the stress components acting on it. And what you should keep in mind is, this is only a representation of what happens in mutually perpendicular planes. It is not a rectangle or square taken out from the model. It has 0 dimensions. So this is a pictorial representation of state of stress at a point. And when I write it in 2 dimensions, this is a tensorial representation of what is the state of stress at the point. See, in those days, people were very, very comfortable with graphical representations. And can you think of what kind of a graphical representation that we can do? In fact, if you look at the history, people have tried various kinds of graphical representation. You have Cauchy's stress quadratic, you have Lamy's stress ellipsoid. Later, you also have what is known as a Mohr circle. We will get on to Mohr circle later, because you will also appreciate the elegance in that. Now, let us go back to our simple axial tension problem and understand what is normal stress in little more detail. Fine. So, we have taken a point P, and then we have also looked at the cross section is taken as A, and we have simply said the stress at this point is P by A. But P by A appeared like a scalar. Instead of P by A, here I have put the force as F, so it is F by A. My suggestion is, always try to represent the stress as a tensorial quantity. How do I write for this? I have determined from my mathematics, from a simple appreciation of what happens to a member subjected to tension, I have determined the stress as F by A. If I go back with the reference axis, actually this corresponds to what happens in the y plane. There is no stress in the x plane. So, I can write this as a tensorial notation as sigma equal to 0, 0, 0 F by A. Is the idea clear? And we will also look at another interesting simple problem. You have a punching operation. In many of the manufacturing, people do it by punching. And this is again a very interesting problem where I have a punch which pierces and I get a disc like this. And I now define the area as the complete perimeter surface of this. So, I have a punch, I can find out what is the force that I have applied to pierce this. So, I can also find out what is the kind of stress happening on this surface. It is actually shearing, fine. And because the problem is simple, straightforward, we can also determine the magnitude of shear stress as whatever is the force F and whatever is the area of the perimeter. I can also say this as F by A. But this F by A, where would I put it in the tensorial notation? In this case, F by A what we have calculated is only representing the shear. Can you write that? We have already looked at how to write a tensorial representation. We have written it in a form, fine. So, I have tau xy and tau yx. So, the tensorial representation of state of stress at any point on this, nothing but what I have this as a matrix. See, shear was difficult. People have not had that idea to start with. So, there is a scientist Parent, he introduced it in 1713 and Coulomb developed these ideas extensively further. So, right now what we will do is we will go back to this simple tension. We will understand it little more. It looks very simple. I have the stress tensor now. You know that you have only just pulled. Now, I said by stress tensor we have the information of totality of stress vectors acting all the possible infinite planes. Now, I have this matrix populated with 0, only one element is non-zero. But for the same problem, if I look at from a different plane of reference, if I look at a different plane passing through the point of interest, I can have a normal stress as well as a shear stress. Though visibly you are not applying a shear stress on the object, but when I look at a plane of interest, so that is what is needed when you want to understand why a chalk fails. When I apply an axial tension, when I apply a torque in different manner, fine. Now, we have already looked at the expressions. So, we have the direction cosine for an arbitrary plane. When I represent this as theta, I can write it as cos theta I plus sin theta j. So, I can find out the stress vector on any plane. We have expression for finding out the normal stress as well as shear stress. Let us look at the quantities one by one. I have the famous Cauchy's formula, Tn equal to sigma into n. So, I get Tnx when I have this multiplied by the direction cosine goes to 0 and Tny equal to f by a sin theta. We will also subsequently see what is the expression for the normal stress and what is the expression for shear stress. And we would like to see a graphical representation. There are multiple graphical representation. We would like to see the stress vector, it is sin theta, and I suppose you know how a polar plot is done. For any value of theta, put it when it is positive in one direction, negative in another direction, and you have the expression, and when I plot this, I have a beautiful plot like this. Is the idea clear? This is one graphical representation. More than the stress vector, from failure point of view, we are interested in the normal and shear stresses. So, we will go and then see what is the expression for the normal stress. You know, you have Tnx, Tny is determined. When you take the dot product, you get the normal stress. Can you calculate what is the normal stress for this? You can check with me later. Please calculate the normal stress acting on any arbitrary plane. Straightforward. So, when I get the normal stress, the dot product gives me normal stress as f by a sin squared theta. And suppose I want to do it as a polar plot, the polar plot will appear like this. See, the problem what we have taken is a very simple one of simple tension, but I have a beautiful plot. The pattern is photogenic, isn't it? And you also get some interesting features of it. What is the maximum value? Suppose I put this as 1 and this as 0. It goes from, when sin theta is 0, you get this as 0. When sin theta is 90, I get this as f by a. So, it goes from 0 to f by a maximum. And we can also write the shear stress. Shear stress diagram is much more interesting to see. Okay. Can you get the expression for shear stress? Because you have the expression for stress vector, you have the expression for normal stress. We have seen tau 1 is nothing but square root of that Tn squared minus sigma n squared. So, if you do that, I get an expression which is very simple. I think by the time I show the slide, you should have your expressions. These are very simple trigonometric simplifications. I get that as f by a sin theta into cos theta. And in order to see this variation, I am not bringing in a scale here. Okay. We will compare these two in the next stage. Let me plot this. When I plot this, this has a beautiful expression like this. So, what do you think immediately once you see a shape like this? Does it look like a butterfly? They are very nice to see, no? See, for environmental sustainability, they say butterflies are needed. Fine. So, what I want to tell you is, when you look at the expression, when you want to do a polar plot, I get beautiful plots. There is definitely beauty attached to this. Nature loves beautiful patterns. But from your point of view, it is very difficult for you to plot and gather the information. Now, what we will do is, we will understand this comprehensively in a single diagram. A simple tension. Here again, I have to caution you one more thing. When I showed you this photoelastic fringe pattern, I have said it is away from the loading points. How many of you noticed it? I do not know. Now, I have also shown it pictorially here. So, we have to worry about what happens near the load application points. Because when somebody gives me an object to apply tension, I can have only an object like this, put a hole, and then I have a provision for me to hold it like this, and then put the pin and then pull it. This is how I can do it. Fine. But my intention is, across this cross section, I should have a uniform stretching. But physically, when you go, you can only do like this. Probably you can improve it further by having multiple holes. Instead of one hole, you go with 2 holes, so that you make it little more uniform, or you go with 3 holes, you make it further uniform, or you also have another system wherein what I have is, I have this, I suppose you are able to see the color, maybe I will put this, it has a different contrast background. What I have is, I have multiple holes, I have about 5 holes. Fine. So, you can try to have your fixtures designed in such a manner that I can go closer to uniform pulling of the member. We would also see that details later. Now, our focus is what happens away from the load application points. Only for the region away from the load application points, I show you the photoelastic fringes. This is again a graphical representation for various loads. That is what you are seeing it. But what you are plotting here is, for a given load, what is the variation of normal and shear stress. Now, I am going to put it in the same graph. I have the normal stress expression as F by A sin squared theta. I have the normal stress plotted like this. So, this goes from 0 to F by A, and you have various points put here, and then you also have the associated plane that is also animated. And if you want to see again, you can have a look at it, because now you can associate this with the particular plane. So, a simple tension can throw you surprises like this. So, in those planes, whatever the representation of stress tensor what you have written will not have zeros in all the places, it can be populated also, fine. And what is the expression for shear stress? I have this as F by A sin theta cos theta, and what is the maximum value this it can go? Only sin 45 and cos 45, I get this as F by A by, the maximum will be 1/2 of what is seen in the normal stress. And this is plotted, the graph is reasonably good, but it should be still smaller than this. But it gives an impression that normal stress is of larger magnitude and shear stress maximum is 1/2 of it. And this graph also can give you additional information. One information difficult to get, see, only when you see these graphs, the beauty is very good. But what I extract from this, certain ideas are difficult to see. Only when you appreciate this, when you go for a simpler representation, you can fully appreciate the beauty of that kind of a graphical representation. Here I can see what happens on a plane, what is the magnitude of normal as well as shear stress. So, from the plot I can find out, I can have a plane where I will have only normal stress, where the shear is 0. That is evident from this. If you are able to recognize, fine. Suppose I go to a maximum shear stress, I have maximum shear stress, that plane also has a normal stress. It is not 0. You do not have a situation where I have only shear stress in any one of the planes. But what we find interesting is, because the way that we have applied the load, that is one thing, but we find you have two such planes where I have only normal stress, there is no shear stress at all. So, these two observations you can make out of this. Okay. Now, what we will do is, we will go back and then re-investigate what is it that we have found out when I have a single hole. You are all now well trained to look at fringe patterns, and what you have here is the full specimen is shown here. You have a single hole, you have 2 holes, and then you have 3 holes, and a blown up of this is shown in this. And if you look at very carefully, I have shown what way the loads are applied. The figure is reasonably geometrically drawn. Can you find out what is equivalent in these 3 specimens? I have shown the length of the arrow indicates the magnitude of the load. Can you just look at that statically? Is there anything that you get out of it? Suppose I find a resultant of this. I have the 2 hole specimen, and you have this forces shown. I have 3 forces shown. Can you find out this from the geometry? You are not able to see that? I am applying the same load. I am just putting it by one force. I have divided the force into half. I apply it at 2 different points, divided the force into 3, and I have applied it. The resultant remains same, fine. And what you see here, I also have this horizontal lines put, And you find near the holes you have beautiful fringe pattern seen, and they all die down here. We have always seen when I apply a simple tension, in the region away from the loading point, uniform color. And what you see in this is, I see the uniform color only after this line when I apply a single load. When I apply two loads, I see it after this. And as I go nearer and nearer that I apply a uniform loading, fine. What I find is the fringe pattern becomes of uniform color earlier than the previous case. And this is embedded in a nice principle which goes with the name Saint Venant. Okay. In fact, he developed this concept in the context of bending stress. See, bending stress, you have to apply a triangular variation. When you have a model, you can only go and apply a bending moment like this. You can't apply a triangular variation by any other gadget. So, the principle is, as long as the load applied is statically equivalent, after some distance from the load application point, whatever the distribution that you are conjecturing is achieved. This is a very useful principle. We will repeatedly use it in solid mechanics. In fact, none of the books give you a pictorial representation in a manner that is represented here. Okay. See, the idea is to have a uniform pull is what we want. And what you find is, by the way that you apply the load, there are local disturbances, and these local disturbances die down after a distance. Fine. And this goes by the principle called Saint Venant's principle. What I have is, I have a single hole, I have a double hole, and I apply statically equivalent force system. The requirement is apply statically equivalent force system. This is a very nice mathematical advantage when you want to solve a problem from a mathematical perspective. So, as long as you apply a statically equivalent system, you can conjecture the similar distribution is achieved at distances away. And this distance can reduce if I make my application of the force system closer to what is intended for. It's a very powerful tool. None of the books really give you any practical demonstration like what you have from photoelasticity here at this stage of development of the course. So, you have the advantage. I suppose you appreciate the utility of Saint Venant's principle. Many times we will simply say Saint Venant's principle, because with the development of mathematics at this stage, it is too difficult to comprehend what is happening near the load application points. Unless you go to a numerical or experimental analysis, there is no way you can find out the forces. Okay. One thing you can notice in all these problems, these corners always remained black. That is a very important clue. Notice this, I will discuss about it in a later class. So, in this class we have looked at further development on the concept of state of stress, and we have particularly focused on the simple problem of axial tension. Even a simple axial tension, if I look at different planes, some of the planes can have both normal and shear stress, and we had done one type of graphical plotting. Polar plot is what we have looked at. The polar plot, the representation was beautiful. Nature really loves beautiful patterns, but to cull out information that we want, it is little difficult for you to do that. And what we noticed was, you can identify two planes in which the normal stress alone can exist. But when I have maximum shear, you always have some amount of normal stress. Thank you.